The big idea in the last video was that we wanted to approximate the area under the graph of a function by taking a bunch of rectangles and adding up their areas. So these rectangle areas weren't going to add up to exactly the area under the graph of the function, but the hope was that it would be pretty close. And the second big idea is that the more rectangles we use, the better an approximation we get. So in the last video, we saw an example where we approximated the area under the graph of a function between x equals a and x equals b by taking the interval from a to b, splitting it up into 4 equal-sized pieces, and putting in a rectangle over each of those 4 pieces. We know the base of each rectangle was 1/4 of the whole distance from a to b, and we needed to decide what the height of the rectangle was going to be. We approximated with rectangles where we use the left endpoint for the rectangle height. What does that mean? We take the left endpoint of the interval, we evaluate the function there, that tells us how tall our rectangle is going to be. This led to this expression that we called L4. The L stood for left endpoint rectangle heights. The 4 was the number of rectangles. And each of the 4 things we add up in this expression is the area of a rectangle. We have f of x0, which is the height of the left endpoint of the first of our 4 intervals, times delta x, plus f of x1 delta x, plus f of x2 delta x, plus f of x3 delta x. Delta x is the base of each rectangle. It's the distance from b to a divided by 4. So the first thing I want to do is tell you what happens if instead of using 4 rectangles, you use 400 or 4,000 or 4 million. Same idea with n rectangles. We're going to write down an expression, Ln, which is going to be f of x0, the height of the first rectangle, times delta x, plus f of x1 times delta x, plus f of x2 times delta x, plus f of x3, plus f of x4. Like, you keep going like this. And where did we stop in the example of L4? What was the height of rectangle number 4? Was f of the left endpoint, which is x3, not x4. So the last term in the sum is f of xn minus 1 delta x. So that's kind of a mess. Let me write this. Plus dot, 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 and then plus the last term, f of xn minus 1 delta x. So what's the idea? What is this delta x here? Delta x is equal to the base of each rectangle. So we have n rectangles, and they take us from the starting point A to the ending point B. So we have to split that up into n pieces. So delta x is b minus a over n. It's the same delta x for each of these n terms. And what happens? So you take x0 equals a, x1, x2, all these points along your interval from a to b, and xn is equal to b. So what is x1? You have this interval where you start at a, and then you move along 1 over n of the way towards the end of the interval. So x1 is equal to x0 plus delta x. Right? Each rectangle has length delta x, and the first one starts at x0 and ends at x1. So x1 has to be x0 plus delta x. And this is x0 plus b minus a over n. x2 is x1 plus delta x. But you know that x1 is x0 plus delta x, so this is x0 plus 2 delta x. And now that we know how long the base of each rectangle is, we can write down an expression for x2 and for any of these xi's. So I'm going to pause and erase, and I'll explain in general how you can write down xi just in terms of a and b and n. We were talking about how we take our interval from a to b and divide it up into n equal size pieces. We need to understand these f of x0, f of x1, f of x2, these function values at these special points that we get by dividing up the interval into n pieces. So how do we write down these special points in terms of a and b and n? And we saw that, okay, the interval from x0 to x1, from a to x1, has length delta x, which is b minus a over n. So that means x1 is x0. You start at x0, and you go forward delta x. So it's just x0 plus delta x, which is x0 plus b minus a over n. Now x2 is x1 plus delta x. But x1 is just x0 plus delta x. So added together, this is x0 plus 2 delta x. So what is x2? It's x0 plus 2 times b minus a over n. x3 is x0 plus 3 b minus a over n. And x4 is x0 plus 4 b minus a over n. That xi is always equal to your starting point, x0, which remember, x0 equals a, plus how far away are you from the starting point? Well, you've divided up your interval into n equal size pieces, and you just go I pieces away. So it's x0 plus I times b minus a over n. So these xi points, these are not mysterious at all. You just start with your interval from a to b, you divide it up into n equal size pieces, and you can write down this expression for what is this xi point in terms of a and b and I. Okay, so we saw this initial expression for Ln. This is the sum of n rectangle areas. We know the base of each rectangle is delta x, and the height of each rectangle is f of x0, f of x1, f of x2. And now we know these points, x1, x2, x3, x4. We know what those points are, so we can evaluate our function there. Let me first say that you can write this expression, Ln, in another way using this sigma notation that you've probably seen before, hopefully in Math 2a. But let me just review. What does each one of these terms look like? It looks like f of x something, f of xi, times delta x. So this sigma notation is saying we're adding up a bunch of terms, and each term is f of x something times delta x, where that I is an index. It's telling us like f of x what. So the first term is I equals 0. So when I equals 0, we get f of x0 times delta x, and then we go on to the next term for I, f of x1 delta x. Then when I equals 2, f of x2 delta x. And the last term in this sum is f of x n minus 1. So below the sigma, you write I equals the first value, and on top of the sigma, you write the last value. This expression for Ln is the same as the one below, but we're writing it now using the sigma notation. This is something we'll use a lot, so you should get comfortable with it. So what have we done so far? We started with this one example of L4, approximating the area under the graph of a function using these 4 rectangle areas. And we said, okay, well, what if you change 4 to like some other number? You can always write down this expression Ln. What happens when you take n rectangles? You divide up the interval from a to b into n pieces, and you put a rectangle over each of those n pieces. What is the sum of those rectangle areas? So let me just write that. So this is the sum of the n rectangle areas. Okay, so in the next video, what I want to do is draw a picture that sort of explains what is changing when you go from approximating with 4 rectangles to approximating with n rectangles, and then also address this issue of the difference between Ln, where we use the left endpoint of each interval for rectangle heights, and Rn, where we use the right endpoint of the interval for rectangle heights.